Hello everyone, welcome to Coast Cup。那大家下午最后一个议程就是谢谢大家来到 Coast Cup。那我们即将为大家带来的议程是 The Next Revolution in Open Source Operating System and System Software。我们讲者是来自 FreeBSD 社群的 George Nevenil。他今天会为我们带来，就是他从很久以前就开始在开源社群经营，然后贡献的故事。然后下面会有就是即时翻译，可是因为它是机器翻译，所以有可能会有一点点的不准，就是大家再请多包涵。那请大家用一个热烈的掌声欢迎他上台。
谢谢。我不知道。I know, it's no fun that way. 你好, and you'll all be very happy that I will give the talk in English. And hopefully that says what I'm saying, but we'll find out in a moment. Let me start the thing rolling on this. So I wanted to talk about the next revolutions in open source. Open source is fairly old now, as you can tell. For some of us, we've been doing it long enough that it's turned us gray. And I want to talk about the future of various parts of software that are really sort of interesting and amenable to working in open source. You can see that I have many aliases. I'm always GNN. So, no open source conference in the last couple weeks should start without this slide. So I think we're all feeling pretty good about open source since we didn't destroy everyone's travel, hospitals, and those various other things. And for those who haven't seen the wonderful CrowdStrike images throughout airports all over the world, you know, those of us who work on open source are like, yes! As long as you weren't at an airport, then you were going, no! But we shouldn't be so smug. So it turns out that modern operating systems and system software are built on very old models of computation and old understanding of computers. They're built on what we like to call unsafe hardware, hardware that allows people to do things like null pointer references, which is what the CrowdStrike issue was. Also a lack of testing, which was the other CrowdStrike issue. They're built with unsafe languages, C and C++. And when I talk about C, I like to explain to people that C is just assembly language with a for loop. It's a very low-level language, and it has very little safety in it. So even though it was really fun to be at home and watch the world melt after CrowdStrike sent out those updates, the same thing could happen to us. It could happen to open source software because we and the proprietary software makers share a history. So let's have a brief history lesson on operating systems. Since I look around, I might be the oldest person in this room, although not quite so old as to be from the 1950s, thankfully. So operating systems are software systems that are developed to make it easy to use hardware. And as hardware became more complex, software became more complex along with it. And so you have early systems like Sabre, which none of you have hopefully ever heard of, the Atlas, which I'll give a special shout out to in a moment, and then Multics. And everyone remembers Multics for one reason, which is Unix, because it was not Multics. But Multics was a really innovative piece of operating system software for the time. It was one of the first operating systems written in a high-level language, well, high level for then. ESPOL, SBOL was a dialect of something called ALGOL. If you have programmed in nearly any programming language that is not a functional language, not Lisp or Scheme or Haskell, then you are programming in ALGOL. ALGOL was developed in the 60s, and from it came every language you have ever programmed in. BASIC, C, Python, Perl, Rust, they are all ALGOL-like languages. And so Multics was quite cool because it was developed in a high-level language instead of what most things were developed in the 1960s, which is assembly. So OS360 from IBM, originally all written in assembly language. DOS, we get to the 70s, DOS and the home computer revolution, which is the late 70s, early 80s, all written in very specific assembly languages. Unix and C developed together, and C and Unix were so successful that from the 1980s forward, which is 44 years, nothing has changed. We still write operating systems in an unsafe language written at Bell Labs in 1969. And this, as we found out this week, and as we continue to find out, is a problem in software for a couple of reasons. So these early systems were developed to be run in the basement of a bank or maybe in a research group. They were not connected to the internet. There was no internet. So we have now taken unsafe software on unsafe hardware, and we have convinced 8.1 billion human beings, which is the entire planet, that computers are a great idea. You should put computers in everything. Put them in your airplanes, put them in your cars, make sure that everything runs on computer. I'm sure all of this stuff runs on computer. And yet, we haven't made them any more safe or any more reliable. So, I want to give a special shout out to Atlas. In particular, now that I'm a graduate student at the ripe old age of 57, I've had to do literature studies of operating systems because that's my research area. And a colleague I worked with for a long time, you would tell him some cool new thing we were doing in operating systems in the 80s or 90s, and he would say, oh, we did that on the Atlas in 1956. And that's just one of those things that you're used to old people like me saying. It's like, oh, I remember. It turns out they did. And if you look up this paper, which I really enjoy, the Atlas Supervisor, it's really short, and everything you've ever seen in Unix, almost everything you've ever seen in Unix, or Multics before it, system calls, protection levels, they're all in the Atlas. It's done in the late 50s. Really quite interesting. It's a great paper. So, let's talk about computers. Because software isn't really useful without them. So what did a computer look like when the current models of operating systems were designed? Well, they were relatively simple. This is a block diagram of the system for which Unix was originally written at Bell Labs in the late 60s. It is really easy to read because it doesn't have a lot to it. You've got arithmetic, you have an optional floating point processor because floating point, that's hard. You have a couple of buses, you have memory, you have a disk, and that was the whole central processor. Really, really simple. And so writing software for it, while a great achievement, Unix is a great achievement, was still something that one person, or in this case, two people, Kernighan and Ritchie, could keep inside their heads. They could understand what the operating system did and how it worked. They'd written most of it. And so what happened since 1972? Well, hardware changed a lot. So first column here is the PDP 1145. That's the machine on which Unix was originally written. And we go up through roughly a couple of decades all the way up to current hardware. Our clock speeds increase. The number of transistors increases. 68,000 transistors in the 68,000 chip from Motorola. 9.5 million in a Pentium 3, 1 billion in a Xeon, 16 billion transistors in a Snapdragon. So if you have an Android phone in your pocket, you have 16 billion transistors in your pocket, which is a ridiculously large number of transistors. And we went from, I mean, cores is kind of silly, like you just saw that diagram. We went from a single CPU, like one thing that could execute one thing at a time, to systems, you know, again, your phone has 8 by 8 cores in it. Lots of memory, lots of storage. Now you've got graphics and a GPU and TPUs, and supposedly you have AI in your phone, which is a really terrifying idea generally. Networking, I mean, the original Unix system had no network, right? There was no talking to anyone. You know, now, I mean, I can wave my phone around. Now, how many networks are in this phone? How many ways am I connected to the world? A lot of them. And at the same time, the cost came down. So I adjusted these costs to if you bought one of these now. So the machine that Unix was written for, if you bought it today, if you could find it, would be $140,000. Your phone costs about $1,200 US if it's a high-end phone, right? So the cost per core, the cost per computing, we know about this has just gone down. But also complexity has gone up. So for us in technology, cost going down is great. When I was a kid, to get my first home computer, I had to work in a bakery for 6 months to save enough money for my first home computer. Now, you know, even if I weren't a working computer scientist, I could have a way more powerful machine for $30 for the price of a few very expensive Starbucks cups of coffee. I could own a computer. So let's talk about complexity. This is what a phone looks like. You remember the earlier diagram of the ALU and the memory and all of that. Right here, that is some generation of Snapdragon that I stole the image off the internet for. But they all look alike. You can't even read, I mean, maybe you can read that if you have really good glasses. You can't even read or enumerate the number of cores that are in this and the number of different functions they do. And so for those of us who write system software and build operating systems, and the system software and the operating system are supposed to be able to manage the hardware on behalf of the programs, well, how do we manage this? Well, currently, what's happening is we're not. For the most part, the bits of open source that we all work on, the Androids and the BSDs and all this other stuff, iOS, which uses BSD, are often relegated, pushed off to a very small number of cores. And if you want to talk just about that, you should go look for a talk by Timothy Roscoe, who's a researcher in Switzerland, and has a really great talk on how Linux and the Unix systems are actually not running all of these cores. These cores are all running little bits of proprietary something, and they're not very well coordinated. So, complexity. So, what happened? Well, we know, so as technologists, we always like to talk about Moore's Law. Like, oh, you get twice as many transistors in 18 months. And isn't that awesome? You've got so many more transistors, you could do so many more things. But we can think about it this way as well. So when we looked at that history, cost dominated, right? So imagine that a car cost, and this is, I apologize, this is a very American or US view, because everyone has to have a car, except me, I live in New York. But imagine you had a car, but the car cost $1 million. Well, you'd really want to share that car with someone else. But eventually, the car gets cheaper, and now you have, well, maybe we should think about scooters instead since we're in Taiwan. I mean, I understand that most Taiwanese have 2 scooters. So, we go from very expensive to much less expensive, and we go from a small number of people using one machine to one person using many machines. I mean, if you tried to count the number of cores that you're walking around with every day, you would be hard-pressed to do it. Just from your cell phone, your watch, any automated thing you ride in, I mean, a car. Cars are now networked computers, which for those of us who work on computers and networking makes me want to ride a bicycle. So the economics change. But the design of the software didn't. And that's part of what we're going to talk about. So what's really changed, right? So we always talk about Moore's Law. You have too many, well, I like to say you have too many transistors. You have way more features than you possibly could ever imagine to use. But, you know, capitalism. The one thing that's messed us all up since about 2006 is the end of what we call Dennard scaling. So everyone likes to talk about the number of transistors, but not the fact that the frequency of your computer does not increase. For those of us in the audience who are in our, whatever I am, you know, it used to be that every year you could solve your performance problem by buying a new computer. Because, you know, for a while your machine was a few megahertz, and then it was 100 megahertz, and then it was 500 megahertz, and if you push the turbo button, it was 650 megahertz, and then it was a gigahertz, and then 3, and then it stopped. So for the last 18 years, processors have been around 3 gigahertz. But the transistors went up. So the hardware people, and some of my best friends do hardware. The hardware people gave us far more transistors, but not any more speed. And so we went to these multi-core designs and offloading a bunch of operations like mathematics or cryptography or graphics or vector calculations for the machine learning people. We created all this offloaded processing, but from a system software standpoint, we don't manage that, right? So Linux, Android, FreeBSD, pick your Unix derivative. That doesn't manage the GPU card. The GPU is running a completely different set of software that is targeted completely at the GPU, and the OS just says, have some memory, and I trust you with it. So we wind up with more cores, more memory, more offloaded processing, more features, but not more coordination, right? And not a better understanding of what the system is doing as a whole. So as system software people, we're kind of falling behind the hardware people. We have fallen behind the hardware people. So what should we be doing? And this is where we get to what are the next revolutions, right? So, for 50 years, we've been taking a well-known model, Unix, and we've re-implemented it, right? So the BSDs were derivatives of Unix. There were as a complete quote-unquote rewrite. Linux, same thing. Android is Linux. But the concepts, everything is a byte stream, right? Everything in a Unix system is a stream of bytes. There is no inherent structure. The programmer has to add structure. It's a really clever idea. It's one we've lived with for 50 years. The fact that everything is a file, open, close, read, write, and then the magic, I/O control, because everybody needs an escape hatch. We have these models, but what other models are there, and what could we be doing now with this modern hardware that would be interesting, and that would be useful, and that would be safe? Those are the things that are really important. So how do we take advantage of this embarrassment of riches, all these transistors that are laying around? Well, we want to exploit the hardware. We should be thinking about new programming models. We should be thinking beyond a byte stream and open, close, read, write. We should retry some old ones. There were, if you look at even the Wikipedia page of the history of operating systems, until the early 2000s, there's a much larger diversity of operating systems, both for research and development. And then you get to this point, it's really funny. I decided not to connect my laptop to the internet because I'm paranoid. But if you look at the page, from 2000 on, there's just columns. One is the BSDs, one is the Linuxes, one is the Androids, and one is Windows. So it's 4 columns, and then there's research stuff on the side. So it's 4 columns of the same thing over and over again for 24 years. Just different releases. But the model doesn't change. So other things we could do. So C was written to address small memory slow computers, right? The reason, I can't remember if it's Kernighan, I think it's Kernighan, when asked what he would have changed in Unix if he could do it all over again, he said he would have put an E on the end of create. But that tells us something. At the time, memory was such a premium that it mattered to leave off a single character. And I can tell you, that doesn't matter anymore. So, new languages, new tooling, we need new operating systems, right? The models that we have now do not address the hardware as it exists today. And I'm an OS person, so I believe in applications in the same way that I believe in the tooth fairy, because applications are way up here, and I'm way down here. But I hear there are new applications. So tooling really matters. In the early days of software development, compilers were expensive and proprietary tools. And then we got the GNU tool set, which was great. GCC revolutionized, it was a previous revolution, software development because it was an open source compiler. Anyone could download it, they could build it, and they could use it. And that was great. And GCC reigned supreme for a long time, but it had certain failings, not the least of which is that it was nearly impossible to extend. And so some people created the LLVM system, which is actually not just a compiler, but it's a compiler toolkit. And that was another revolution in open source. LLVM allows the creation of new languages, and we'll talk a little bit about that. But tooling matters. Having good tools makes it easier to build better things. If you had to build a house with a screwdriver and no hammer, you'd be really bummed. There's been a lot of work recently in formal verification, systems like Coq. They're used to mathematically prove things about software, which is quite useful if you want to actually prove whether or not something is going to work. Tracing has been really helpful, dtrace, eBPF. IDEs have brought a lot more people into building software and have made software easier to build. These are all open source things that revolutionize software. And they are areas in which we still have work to do. You'll notice I put a ... under debuggers because really GDB and printf are the only two things people still seem to use. I think there's work to be done there. I talked about LLVM and how LLVM revolutionized the ability of people to build new languages. In particular, Rust. I mean, there are other languages, and actually if you look at GitHub statistics on language uptake, Rust is still fairly small, but in the systems community, it's pretty big. For anyone wanting to build a new operating system, most of us are looking at Rust. Why? Because Rust does things that C doesn't. And generally, unless you tell Rust to do something unsafe, Rust will not let you do something unsafe, and so you don't wind up with the CrowdStrikes of the world. It isn't perfect, but it is the next step in the right direction. Go, which was developed by Google, all enabled by this new compiler toolkit. Tooling matters. So I want to talk briefly about ideas that people should look at, right? So we're talking about what do we do next? What are the next revolutions in open source? Well, I'm a big fan of history, depressing though it is. And so I want to talk about some old models that might have new life. One that certainly does. Capabilities, and then related microkernels and message passing. But let's talk about capabilities first. What are capabilities? So one of the things that makes C and current computers unsafe is the fact that a pointer in memory is just a number. I can add to it, I can subtract from it, I can multiply it, I can manipulate it in many ways. And once someone is able to manipulate a pointer, that is a security problem, and that results in a lot of problems for us. Capabilities were an idea that was developed in the 1970s, actually, as a way of saying, well, we don't want just pointers. We want actual, like, cryptographically signed nonces, which means I can't add 1 to a capability and try to get at your memory. Right? If I add 1 to the capability, then the computer says no, and you get a fault. So they confer access based on cryptographic operations. They allow you to do valid ownership. So for instance, one of the classic problems is image manipulation libraries, right? libjpeg, all of these things have passed these pointers around, and they're a very common way to break into someone's phone. So you want these things. The problem is, at least at the time when this was done in the 1970s, they increased the size of a pointer. So if you imagine that you have a 64-bit machine, in order to have these capabilities, you have to have more metadata. And in a system I'll talk about now, we doubled the size of a pointer. But if you really want fat pointers, you can wind up with like 256 bits. Now, when you don't have an embarrassment of riches, that's more of a problem, because now you're trading, you're economically trading how much data you can put in the computer versus how safe the program is. So these are an idea that has come back. There is a research project that has produced an actual computer at the University of Cambridge. That's called Cherry. They are extensions to the instruction set to give you capabilities. I'll talk a bit about that as we go on. But let's take a look. So on the left is an actual computer built to do capabilities. This sits in the foyer of the computer lab at the University of Cambridge. This was built in the 70s. I was 9. And on the right, we have a processor designed by ARM and built down the road at TSMC, which actually has capabilities in it. And this is called a Morello processor. So let's talk a bit about that. So I talked about this embarrassment of riches. Well, in 1976, the CAP computer was a complex instruction set machine built from TTL logic, like not from LSI even. Completely custom, 32-bit processor, 256K of RAM, which was a huge amount of memory at the time. And it had its own operating system, file systems, everything coded in assembler, of course. And then fast forward to 2022, when we were 23, when we were able to get the Morello chips built. And you've got a RISC processor made out of VLSI. It's a modified ARM design, so we didn't have to build a whole new processor. We went to ARM and we said, hey, how about adding these extensions? And they said, oh, well, how about giving us a lot of money? And we said, well, how about the government gives you a lot of money? And they're like, okay. And away we went. It's a 64-bit ARM V8-based processor. You can have 64 gigs of RAM. It talks to the standard bus. It looks like any other desktop or server PC that has an ARM board in it, ARM chip in it, that you would see today. But it has these enhancements that allow you to do these really great security things. So for instance, there's a public paper in which Microsoft studied like a huge number of their known security issues. And just running the software on Cherry, and having recompiled it, of course, would have removed 70% of the security issues that they know about. Because no more pointers. So, let's bring that back to open source. This is an open source desktop. This is Cherry BSD. You see the link in the bottom. Capability enhanced, running on top of Morello. You can download this and run it in QEMU today, and you could play with capabilities and see how they affect your software. You could compile using the LLVM compiler, which has been modified to understand Cherry. You could recompile your software and try it and see what happens, right? See which pointer problems you have and all of those things. And this is all completely open source. We just cut, well, since I'm the release manager, I just cut the most recent release, and that's up on the website. By the way, I forgot to mention one thing. The little, oh, that's in the wrong place. Can we get rid of the bird? I mean, I could fix this. Hang on. Is there anyone where it's on the left? No, I changed the master. Can someone try and scan that? I see Philip's trying to. Yeah. Okay. So if someone can post, so I put the 2D barcode up so you could ask questions, but someone gave me the bird, so that's how that's going to work. Anyway. Okay. Posted the link. Thank you. Yep. Can you get rid of the bird? It's the magic of technology. And now I need the top of my slide back, though. All right, so if people want to scan that, that allows you to ask questions. I should have mentioned that earlier. I also should have noticed the bird. All right, now what happens when now I need a, can you bring that back? All right, so we talked about capabilities. I'm going to let him do that while I talk about message passing. So one of the interesting areas that was studied in the 80s was whether or not you could take a really large, complex piece of system software like a Unix kernel and break it up into smaller things. And this was done most famously by Mach. Mach was developed at CMU, and they used message passing to move many of the kernel services out of the kernel, because kernel programming is hard, but also when you make a mistake in the kernel, everything dies. And so We tried to take some of the services out of the kernel and move them aside. And we did that by doing message passing. So Mach is very famous. QNX was an embedded operating system, real-time operating system that used a similar mechanism. This resulted in what we called microkernel designs. And my favorite comment about this was from someone who said that, you know, in the 1970s, everyone got funded by DARPA and all these other research groups to put things into the kernel. And then once we had message passing, they got the same amount of funding to take it out of the kernel. But, you know, that's how funding works. So microkernel design. So macOS, actually, which is based on BSD and parts of Mach, actually had this. And it's been progressively removed. And if you look at the manual page from Apple on the message passing system and ports and all the stuff that comes from Mach, they say, well, yeah, it turns out it's not very performant. Like, it's not very fast to be passing messages around. Why is that? Well, before Apple, see the guy in the tie? That's Steve Jobs. So before he went to Apple, he had a company called Next. And Next took Mach and put it onto a 68,000 based Motorola processor and created this thing called the Next Cube. And this was a Unix machine you could have on your desk. I think it only cost $5,000 US at the time, which is probably $15,000 now. It was a very expensive toy. But it was a uniprocessor, right? It's at a time when there were no multi-core machines. And so that means that the performance being measured was messages being passed on one processor. Well, what does that look like? And I'm going to do this. So, welcome to the Olympics. You probably all know who this is, famous Taiwanese ping pong player. Message passing on a uniprocessor is like playing table tennis with yourself. Right? Because every time you want to send a message to another service, there's no other processor. It's just you. So you create a message, you put it in memory, and then you give up the processor, and someone else, some other task, takes the message out, reads the message, and sends it back. So you're playing table tennis with yourself, which is, as you can see, really exhausting, and also not high performance. So at the time that Mach was built, there wasn't hardware that could actually exploit what was going on. So move to today, where you have these multi-core machines, and instead, on a multiprocessor, everyone can do more work. This is Taiwan's badminton team, or one with the badminton doubles, I believe, beating China. And in a multiprocessor, everyone can be working in parallel, right? If you have 32 cores, and I mean, this machine has, I don't know, 12, 16 ridiculous number of cores, that means that it's not, I create a message and give it to myself. I create a message and give it to that other core, which has had nothing to do until I give it a message. That means that this model could be performant on modern computers, but we need to try it, because currently we've taken all of that out. So those are some old ideas that I think we should be looking at. Oh, I'm under time. I'm on time, which is good. Let's talk about a few new areas to explore. And so one of the things I wanted to highlight in this talk were other open source projects that were in these interesting areas. So I talked about capabilities, but the capability systems that I just showed you are big server-like systems. That the Morello box is 32 gig, 64 gig box sitting either next to your desk or in a rack. Some folks took those ideas at Microsoft Research and they created something called Chariot. Open source projects always have to have really cute names. And also, you always need like a penguin or a demon, but I don't do branding. So I'm sure they have something cute and it goes on t-shirts, but I have no idea what it is. So Chariot, capabilities for small systems, right? It's a hardware, software system. Microsoft Research created an actual hardware design that the software runs on. Again, it's another set of the capability extensions to an instruction set. It's all in C and C++. Well, okay. It's MIT licensed, which means anyone can grab it. And there's now a company that's going to build these chips based in Cambridge. But if you want to find out anything about it, you can look up chariot.org. If you want to look at the OS they built, which is a much smaller, it's not a Unix system, much smaller system, you can look at their GitHub page. So new ideas. Another project that I work on at the University of California at Santa Cruz is called Twizzler. And so back to the embarrassment of riches with transistors. What are we going to do with all these transistors? Well, one of the things people did with transistors was they made these things called NVDIMMs, non-volatile DIMMs. So imagine you had a computer that when you turned it off, didn't erase RAM. Almost everything we have to do in the operating system is there to make sure that if you ever turn off the computer, the state in RAM is stored somewhere else, usually in this thing called the file system, which I don't know how that works, but it's pretty cool. So one of the, we like to call these conceits in research, is that data now dominates, not code, right? So back when Unix systems were built, the code of the operating system and the code of the application was a significant amount of what was being in memory. Now that's totally not true. What fills your memory is pictures of cats. That was a joke. Anyway, what fills your memory is all of the data that you're operating on. It's all of the machine learning data. It's all, the gigabytes of RAM are not for the operating system and not for the application. They're for the data. So if data dominates and not code, why not build an operating system around data? And Twizzler is an operating system, greenfield, built in Rust, 100%, currently being actively developed, BSD2 closed license, Twizzler.io is the link. And its entire reason for existence is to make it so that it is easy to operate on data as if there is no file system. You just operate on the data and things, quote, just work, unquote. Now it is software, so there are bugs, but it's a different idea. It's a different way of thinking about processing data. This is something I've personally worked on. So kernel data as a database. So we now have one of the cool things people did, one of the earlier, more recent revolutions, was all the tracing stuff. So dtrace and eBPF. You can now look at the state of the system transition as it runs with relatively low overhead. That's great. But one of the things that people don't quite realize is the kernel is full of data, right? If you want to know the state of the system, you have to ask the operating system, like, well, tell me about all your processes. Tell me about your sockets. Tell me about this. Tell me about that. But that data is just sitting there in the kernel. And we've written, over 50 years, a bunch of ad hoc programs to extract that data as strings, which are a really terrible way to operate on data. So the nice thing is that kernel data is relatively simple, because when we started writing kernels, you couldn't put a complex data type in there because it would slow the system down. So kernel data, what's inside of FreeBSD, Linux, whatever, is just a list of structures. They're just lists. Sometimes they're even doubly linked lists if we want to waste memory. So they're lists of structures. There's some trees, but not many. And so we realized that what we could do is we could take two open source projects. We could take SQLite, which is an SQL embeddable database. It can be inside of an application. And we put it in the operating system. We put it inside the kernel. And then we started exposing all of the kernel's data tables as SQL. So for anyone who's ever done SQL, I can now do a join on two different disparate kernel data structures, which you've never thought to do before, just because I exposed them through SQL. As of about 4 hours ago, we submitted our first paper on this to a conference. We'll see if they like it. But it's another way of thinking about system software, thinking about the kernel as data, as opposed to just what functions get executed. And then last, something I'm working on for my late in life PhD, is something I like to call zero. And I got cautioned by my advisor that it's very important to pick the name of your projects correctly. I don't think he likes zero, but too bad. Because in computer science, we count from zero. And so we're starting from zero again. And the ideas here, which will be studied over the next however long it takes me to finish my PhD, are some ideas that have been studied before, but not in depth. So most operating systems are shared everything. Once you put something in the kernel, it is there forever, and everyone can touch it. There's only one boundary. That was the thing that changed between Multics and Unix. Multics had many, many protection rings. like 16 or 8, I forget now, I have to look at the manual. One of the simplifications of Unix, because they thought that Multics was too complicated, was, look, you can be in user space or you can be in kernel space, and that's it. And now we have virtual machines, so there's sort of a sub-basement that nobody talks about. In Zero, we don't do that. In Zero, you must declare who you are talking to. You want someone else's memory, you have to create a connection to it. And it has to be validated. It's being done as a microkernel design. I like to call it a femtokernel because there's just going to be very little kernel space. It will allow you to choose your bindings. So one of the biggest problems in extending an operating system is that, let's say you create a new device driver. So, Bob's company comes up with a new network chip, and then Bob makes me write a network device driver again, which I hate. Once you load that driver in memory, it can touch every other driver. In fact, operating systems, so for all of you who've ever taken an OS class, there are all these great things you're taught in OS classes. You talked about the scheduler and the memory manager and all this cool stuff, and it turns out that's 30% of the operating system. In FreeBSD, 60% of the operating system is device drivers. I'm told in Microsoft it's 90%. So all the cool stuff you've ever learned about operating systems is way over here. And everything else is these horrible device drivers that just go poking around in memory. So one of the problems we have is once you load something in memory, you're stuck with it. In Zero, we're going to allow you to choose your bindings. You could actually have a mock-like service just by turning a switch. Anyway, this is going to be built in Rust because I've decided to learn one more systems programming language before I die, and that's it. After Rust, I can go. Please don't make me do another one. All right, so let's talk briefly about brownfield versus greenfield. So this is one of the big challenges, and this is the reason that Linux and Unix and BSD and all that stuff have dominated for so long. It's not that other people didn't have interesting ideas. They had interesting ideas. There was Amoeba, there was Sprite. SEL4 actually got traction, which is great. There was the V kernel by Charton. There's like a long list of fascinating research operating systems. And I can tell you, when you work on a greenfield system, especially if you work in a company, and you're like, well, we had these great ideas, and look how the hardware works, and it's so much better. And then someone from marketing says, what about POSIX? And then you're like, oh, I guess we'll build a POSIX layer. And then it's all over. So that's greenfield. The most successful projects have been what we call brownfield. So a brownfield takes a currently existing system and extends it. Mock was a brownfield operating system, right? So they used 4.3 BSD at the time to provide a lot of the services they didn't want to build. Linux is the ultimate brownfield, right? They went and re-implemented the ideas from Unix. The BSDs are derived from earlier Unixes. And then Windows, whatever, right? Like as far as I can tell, Windows is just DOS with more and more layers on top of it with terrible user interfaces. Just my personal opinion. But those are brownfield systems. And so how do we, I'm almost done, I promise. So for those of you who didn't study Greek mythology, which in a room full of computer programmers is probably all of you, one of my advisors is an English major. Now he's a computer scientist, but his undergrad was English, so he knows this stuff. The Ship of Theseus. The Ship of Theseus is a philosophical question based on ancient Greek mythology. Supposedly, after beating the Minotaur, whoever beat the Minotaur, they took the ship of the king, Theseus, as a war trophy back to Athens, and they kept it and maintained it for however long it was. Well, of course, Ship of Theseus is made of wood. So if you keep it as a war trophy, you have to keep replacing bits of the wood. And the philosophical question is, if you keep replacing bits of the ship, when is it not the Ship of Theseus? And so in our approach, like the OSDB approach or these various things that I'm talking about, brownfield, we can go in and replace bits of Linux, BSD, pick an operating system, it doesn't matter, with new features and leave the shell. And that is the Ship of Theseus approach. And that approach is the one that is most successful long term. I love greenfield. I would like to be left alone for 5 years with $1 million to just write OS code and not have to give it to anyone. If anyone has $1 million, see me after the call, after the discussion. It's unlikely to happen. So Ship of Theseus is one of the ways of thinking about how do we keep replacing the bits. For those of you who don't like Greek mythology, The same philosophical problem exists in the transporter from Star Trek. If I take all of your molecules and I turn them into energy and then I turn them back into matter, are you still the same person or did I kill you? All right, so we've come to the end. Where to from here? Where will the next revolutions in open source come from? I argue that given the embarrassment of riches with hardware, that we need to see more software that addresses modern hardware. I don't really need to re-implement Unix ever again. I've done it before. You don't need to do it either. So we need to exploit the hardware, try new programming models. There are certainly a ton more ideas than the ones I talked about today. Retry the old ones. Go look at your history. Look at what researchers did before. And think about, oh, well, that was running on a VAX, which is an ancient computer from before any of your time. The VAX was too slow to do that, but maybe my new machine is fast enough. Think about new languages, especially, please, more safe languages. If I never see another segfault as long as I live, it'll be a happy day. New languages, new tools, new operating systems, and I hear new applications. Thank you. Actually, if there are questions, do you want to take one of those? Yeah.
Thank you, George, for the talks. And we have the question link that we post on the Telegram, but I think maybe someone didn't see it. So we have one question from the audience. Is there anyone want to ask question? 有人想要问问题吗？然后现在就是想看 Slido 问题的人，就是请大家投票，我们待会会就是读2个 Slido 的 question。
Thank you for your talk. One question is, like, if I interpret the history correctly, one reason that Linux, for example, was so successful is that it kind of re-implemented Unix, but the success was the fact that you can run Unix applications on Linux as is. And like the same as you said, like software is useless without hardware, a new operating system is useless without applications. So how do you propose to address the lack of applications of this new operating system design? Because we talked a lot about community in this conference. So like you also need a community of application developers to kind of make it useful.
Sure. So yes, it turns out that operating systems aren't very useful without applications, except for those of us who just like operating systems. So there are two paths. As I made the comment about marketing asking for a POSIX layer, you wind up with a POSIX layer. But I think that at this point, while there are many applications that work well because there is a POSIX layer or a Windows layer, I mean, I don't use it, but I hear people do. There are applications that need to be written that are not to that layer. And that's the thing to enable. So especially, I spend a lot of time in the embedded world, a lot of the machine control systems, a lot of the things that actually operate the world, people have been trying to, wedge POSIX into that. And actually, I think that's the wrong approach. I think the approach there is that you need to have, and it would be great to see a community of people built up around new programming models. We're hoping to do that with the data-centric stuff with Twizzler, obviously. I think there has to be both. As someone who once tried to use Plan 9, which is, Plan 9 was after Unix. And then we tried to use Plan 9, and oh, well, LaTeX doesn't work, so I can't write the paper I need to write because there's some missing POSIX bit. There is always the second system problem of where do you get the applications from. I think we don't really have a problem with sort of server-based POSIX applications. I do think we have a problem with the way applications are currently written for things that are on battery power, right? So the amount of work that is required to make a phone not melt or run out of battery, in part is because people have to trick the operating system because the applications are POSIX. And so there need to be new models there. The question is so continuation programming in different ways. In terms of community, that's the beauty of open source. The ideas that take off will actually have community around them, and there are alternative to POSIX programming models that do have communities. They're much smaller. But one of them will be successful.
Okay. And we got some questions from Slido. The first one is, do you think the post-like abstraction of operating system needs to be replaced in order for us to use modern hardware's more efficiency?
Yes. Well, I mean, that was kind of the talk. So, I mean, in order to use modern hardware, I mean, this is what we're finding is that if you don't do that, then the POSIX-like systems will be moved to maybe a control processor or an adjunct processor, and someone's proprietary firmware will run on the other little cores.
Okay, and the next one, since we cannot see the code base easily, how can we study OS which is not open source, like Windows or Mac OS?
Wow. So there's a software from the NSA called Ghidra. You could disassemble it. So there are a few ways to do that. Actually, I joke about using Ghidra to disassemble operating systems. But now, modern operating systems are fat. They're very, very big, millions of lines of code. But if you want to understand a bit of the operating system, you can do what we did when I was a kid. So when microcomputers were 64K, we would print out on paper the assembly language of the operating system, and we would take a pen and we would go through line by line and figure out how a Commodore 64 worked and an Apple II worked. Now, I wouldn't recommend doing that for Windows. It would take I mean, there's a lot of people in this room. Like, if you crowdsource it, you could probably do it. But you can find the core algorithms, right? The APIs are documented, because otherwise you can't write a device driver. So if you want to know how a bit of Microsoft Windows works, you can reverse engineer it. And I don't want to do that, but other people can. Yes.
OK，我们再读一个 Slido 的问题，然后最后开放一个现场问题。The next one is, will RISC-V change the world?
Nothing ever changes the world. The world is a depressing place. I think RISC-V is an interesting system. We will see whether or not the economics matter. RISC-V has done one thing that is really useful, which is it has replaced MIPS as the research instruction set architecture. So until RISC-V, anyone who wanted to do hardware software research had to use MIPS, because it was the last patent not encumbered instruction set architecture in the world. RISC-V is similar, and so RISC-V will help researchers. Will it change what's on your desktop? I'm not an economist.
OK, and I would ask, is there any questions?
Okay, hi. I have one question. As you said, the OS haven't to change a lot since many years. But right now, you know, the hot topic is AI PC. So I don't want to talk about not Copilot, not application level to look at. Is that possible? We have AI PC OS, for example, like you already mentioned about the database as the part of the operating system. That is a good idea, but can we, or maybe you already think about, or any other people think about, we have AI PC operating system. We have a shortcut and kind of some redundant, or maybe something wrong on the background or something like that. Can you give me some idea?
So the AI PC question. Well, I was at Guangha yesterday, and according to Microsoft, their new OS has AI in it, which is really terrifying, mostly because it's probably stealing your password. So there are a few ways to answer the AI and OS question. First of all, it depends on what you mean by AI. So this phone and most phones do, machine learning, right? And so you already have that in the machine. Is it governed by the operating system? Not particularly well. Now, if you're talking about the current fad in AI, which is large language models, the only thing you will have that you, as a person, would use is consumption of an LLM. right? So the LLMs, the large language models, will be generated in a data center somewhere. But your operating system, and in particular your mobile operating system, is very likely to consume some component of a large language model to do things like translation. Now, of course, if, you know, please don't give a long sentence. Actually, how's this thing doing? Yeah, there you go. I suspect the one place you would see an AI-like application will be federated large language models in mobile for things like fixing your photographs, because almost all of the sort of vector graphics, the vector processing in your phone is to make your photographs not look bad, and language, basically translation. So I think you'll see it there. Will that be exposed to the operating system? A little bit. It'll have to be, because you'll have to do what we call split or federated ML. The big part of machine learning will sit in a data center somewhere, and your phone will do the last little bit. So I think that's where you would see it.
Okay. 谢谢 George 为我们带来这么精彩的演讲。Thank you George for give us such amazing talk.